Have you ever watched a rocket launch and just wondered, how does that even work? Well, today, we're going to dive deep into the heart of that power, the cryogenic rocket engine. It's an absolute marvel of engineering, but wow, is it one of the toughest things to get right.
And you know, it's really not an exaggeration to call this the absolute pinnacle of rocketry. Think about it, only a handful of countries have ever managed to build and fly these things. It's a very, very exclusive club in the world of spaceflight.
Okay, so what is the big deal? I mean, why is making something incredibly cold the secret to unlocking all that power to get to the stars? Well, let's get into it. All right, to really get why cryogenic engines are so special, you first have to understand the fundamental headache of all rocketry. It's this constant battle, right? You need a ton of power to fight gravity, but the fuel that gives you that power is heavy, and you have to lift that fuel too. It's a real catch-22. So, in the world of rockets, there's one number that matters more than almost any other. It's called specific impulse. The easiest way to think about it is like fuel efficiency for your car, your miles per gallon. A higher specific impulse means you get more bang for your buck, more push for every drop of fuel, and that is the name of the game. So how do you get that amazing fuel efficiency? Well, the recipe is actually pretty simple. In theory, you need two things. First, a fuel that burns crazy hot. Second, the exhaust gas coming out the back needs to be as light as possible. You put those two together, hot and light, and you get a super fast exhaust. And a faster exhaust means a more powerful rocket. Simple as that. Okay, so based on what we just said, hot and light, there is one element on the periodic table that is just the undisputed champion, the perfect rocket fuel. But, of course, there's always a catch, right? And this one, it's a big one. And that perfect fuel? That's hydrogen. I mean, just look at this. It's the lightest thing in the universe. It burns super hot, and hey, as a nice little bonus, it's clean and won't corrode your engine. On paper, there's literally nothing better for getting that high specific impulse we're chasing.
So, here's the catch. Here's the big problem. At room temperature, hydrogen is a gas. A very, very thin gas. And if you tried to pack enough of it into a tank to fuel a rocket, well, the tank would have to be so ridiculously huge and heavy that the rocket would just sit there. You'd completely lose any advantage. And that brings us to the brilliant, super cold solution, cryogenics. You see, the only way to fix this volume problem is to swap it for a temperature problem. The idea is, if we can get that hydrogen gas cold enough, like really cold, we can shrink it down into a dense liquid. And when I say cold, I mean, look at this number, -253 degrees Celsius. Let's put that in perspective. That's not just colder than Antarctica. It's just a whisker away from absolute zero, the coldest anything can possibly get. That is the extreme we're talking about.
So how do you even get something that cold? Well, it's a whole process. You basically squeeze the gas really hard, cool it down a bit, and then, here's the magic trick, you let it expand super fast. This rapid expansion makes the temperature just plummet, and boom, you get liquid hydrogen. And by the way, you have to do the same thing for the liquid oxygen you need to actually burn the fuel.
Okay, so great, we've got our super cold fuel. Problem solved, right? Not even close. Now we hit what might be the single biggest engineering nightmare of the whole project. How on earth do you pump that freezing cold liquid into a chamber that is literally on fire?
Now seriously, just pause and think about that. You've got a liquid colder than deep space, right next to a fire burning at 3,000 degrees Celsius, and all that's separating them is a thin wall of metal. Dealing with that absolutely insane temperature difference, that's what makes building these things so ridiculously hard. The solution is a little piece of engineering genius called the turbopump. Picture this. It's got a tiny turbine inside that spins at tens of thousands of RPM. We're talking faster than a dentist's drill. That turbine drives these powerful pumps that shove the fuel into the engine. And the most brilliant part? The whole thing is powered by a little bit of the same fuel it's pumping. It's a self-powering marvel. Now, how you power that little turbine is where you get into different flavors of cryogenic engines. You've got a few main designs or cycles. The simplest one is the gas generator. It works, it's reliable, but it's kind of wasteful because it just vents the exhaust from the turbine overboard. Then you've got the king, staged combustion. This one is way more efficient and powerful because it takes that exhaust gas and feeds it back into the main engine to get more thrust. But it is so much more complicated and harder to get right. So choosing a cycle is this big trade-off between power, complexity, and cost. And this is where the design gets just beautiful, really elegant. They hit two birds with one stone. Before the super cold hydrogen goes into the combustion chamber, they run it through these tiny pipes all around the engine nozzle. So what does that do? Well, it cools the nozzle down so it doesn't melt, and it warms up the fuel so it burns better. It's just brilliant.
All right, so we've got the basic concepts down. But mastering this stuff, that means facing a few you could say final boss level challenges. These are the tricky little details that really make or break an engine program. So you've got three big ones. First, controlling that turbopump. It's like trying to tame a wild animal. It's powering itself, so getting it to run smoothly is a huge control problem. Second, you've got that thermal stress we talked about, the constant tug of war between hot and cold that wants to rip the metal apart. And then there's a weird one, hydrogen embrittlement. The tiny hydrogen atoms can literally wiggle their way inside the metal parts of the engine and make them brittle and weak. It's a really sneaky problem. And that's why this quote is so perfect. Calling the turbopump the heart of the engine isn't just a nice metaphor, it's literally true. It's pumping the lifeblood of the rocket. If that heart stutters for even a millisecond, the whole thing comes apart. Everything, and I mean everything, depends on it working perfectly. Okay, let's switch gears for a second. Have you ever seen one of those thermal camera videos of a rocket launch? You see that blindingly hot exhaust plume, right? But have you ever stopped to think about what's going on just a few feet above it, inside the engine?
This right here is maybe the most unique challenge for cryogenic engines, the insane temperature gradient. That's a fancy way of saying how quickly the temperature changes. It's not just hot over here and cold over there. It's going from 3,000 degrees to minus 250 in the space of a few inches. Finding materials that won't just shatter under that kind of stress is a massive, massive challenge.
So when you look at it all together, from taming the perfect but difficult fuel, to building a machine that lives at both the hottest and coldest temperatures in the solar system, a cryogenic engine is really a story about mastering extremes. And that just makes you wonder, doesn't it? As we start looking towards Mars and even further out, what new, even crazier extremes are the next generation of engineers going to have to conquer?
Get ready for the future. Welcome to TechgayanPro, where our innovation takes flight. From cosmic launches to exploring the depths of technology, we're constantly pushing boundaries, counting down to what's next. The future is here, and I'm inviting you to welcome 2026 with us.